Hello learners, on behalf of Indira Gandhi National Open University, we welcome you to this interactive video lecture session. Today's topic is Regenerative Cycle. I am Subhasis Maji, Professor in School of Engineering and Technology from Indira Gandhi National Open University. This topic, that is Regenerative Cycle, is the 25th module of the course Thermodynamics and its Application. Dear learners, we have discussed in detail the steam power plant, where we have discussed the four main components of steam power plant. First one is boiler, second one is turbine, third one is condenser, and fourth one is pump. The boiler is producing high temperature, high pressure steam, and that high pressure, high temperature steam is entering into the turbine, and the expansion takes place inside the turbine. In turn, the turbine is producing work. The shaft of the turbine is coupled with the shaft of the generator, which is producing the electricity, and the low pressure, low temperature steam enters into the condenser, and it condenses into water. After that, the water is pumped back to the boiler with the help of pump. So today's discussion is regenerative cycle. We will see how we can improve the efficiency of the Rankine cycle by adding extra features, that is extracting steam at different stages in the turbine. After listening to this video lecture, you will be able to understand the concept of regenerative cycle. You will be able to explain the efficiency of regenerative cycle, and you will also be able to describe the advantages and disadvantages of regenerative cycle. Dear learners, let us begin our discussion. The practical ideal regenerative Rankine cycle is achieved by extracting steam from the high pressure turbine at various points and is used for heating the feed water. The device where the feed water is heated is known as regenerator. The regenerator also deoperates the feed water, which is necessary to prevent corrosion in the boiler. The flow diagram of the regenerative cycle with saturated steam at the inlet to the turbine at state 1 and the corresponding TS diagram are shown in figure 1 and figure 2 respectively. For every kg of steam entering the turbine, let A1 kg of steam be extracted from an intermediate stage of the turbine where the pressure is P2, and it is used to heat up feed water of 1 minus M1 kg at state 8 by mixing in heater. But dear learners, you must remember that the initial pressure of steam before entering into the turbine is P1. The remaining 1 minus M1 kg of steam then expands in the turbine from pressure P2 at state 2 to pressure P3 at state 3. When M2 kg of steam is extracted for heating feed water in heater 2, so 1 minus M1 minus M2 kg of steam then expands in the remaining stages of the turbine to pressure P4 gets condensed into water in the condenser and then pumped to heater 2, where it mixes with m2 kg of steam extracted at pressure P3. Then 1 minus m1 kg of water is pumped to heater 1, where it mixes with m1 kg of steam extracted at pressure P2. The resulting 1 kg of steam is then pumped to the boiler, where heat from an external source is supplied. Heaters 1 and 2 thus operates at pressure P2 and P3 respectively. The amount of steam M1 and M2 extracted from the turbine are such that at the exit from each of the heaters, the state is saturated liquid at the respective pressures. Now, dear learners, please see the diagram. This is the flow diagram of regenerative cycle with 2 feed water heater. You just see that 1 kg of steam coming out from the boiler entering at state 1 into the turbine. The pressure at state 1 for the steam is P1. There is expansion in the turbine, and at state 2 m1 kg of steam is extracted at pressure P2 from the turbine to heat the feed water, and it is entering into the heater 1 for transferring the heat to the feed water. Now the remaining 1 minus m1 kg of steam is further expanding in the turbine, but at pressure P3 again m2 kg of steam is extracted at pressure P3 and entering into the heater 2 for transferring of heat to the feed water. Now the remaining 1 minus m1 minus m2 kg of steam will further expand into the turbine, and it will leave the turbine. After that, it will enter into the condenser at pressure P4, and then the steam will condense at the outlet of the condenser, and the pump 1 is pumped that amount of water, that is 1 minus m1 minus m2 to the heater 2, and there is heat transfer from the steam m2 coming out from the turbine at pressure P3 entering into the heater 2. After the heat transfer, then 1 minus m1 kg of steam will come out from the heater 2, and the pump 2 will pump that water to the heater 1, and there will be heat transfer between the m1 kg of steam which is coming out from the turbine. At stage 2, there will be heat transfer from steam to the feed water, and lastly the 1 kg of steam will be pumped by the pump 3 to the boiler. Now you see that in this diagram, so there is work done by the turbine, and we will see how we can calculate the work done by the turbine. We shall also calculate the work done by the pump. Here you see there are 3 pumps: WP1, that is pump 1, pump 2, work done by the pump 2 is WP2, and there is also a pump 3, and work done by the pump 3 is WP3. Now let us see how we can calculate the work done by the turbine, work done by the pump, and the heat added to the water in the boiler and the heat rejection in the condenser. Now this is the TS diagram of regenerative cycle with 2-feed water heater. You see that 1 kg of steam is entering at the inlet of the turbine. At stage 2, M1 kg is leaving the turbine and entering into the heater 1. The remaining 1 minus M1 kg of steam is further expanding in the turbine, but at stage 3, that another M2 kg of steam leaves the turbine and enters into the heater 2, and the remaining 1 minus M1 minus M2 kg of steam, there will be further expanding in the turbine from state 3 to state 4, and here at point 4 is the entry point of the low pressure, low temperature steam finally coming out from the turbine and enters into the condenser. And 4 to 5 is the process which is going on in the condenser, and 5 to 6 is the pump work by the pump 1, 7 to 8 is the pump work by the pump 2, and 9 to 10 is the pump work by the pump 3. Now let us see how we can calculate the work done by the turbine, work done by the 3 pumps, and heat added to the water inside the boiler, and also heat given out in the condenser. Now let us calculate the efficiency of the regenerative cycle. So WT is equal to 1 into H1 minus H2 plus 1 minus M1 into H2 minus H3 plus 1 minus M1 minus M2 multiplied by H3 minus H4, and unit is kilojoule per kg. The first part of the right hand expressions for the turbine work is 1 into H1 minus H2. This is the work done by the turbine from state 1 to state 2, where 1 kg steam was there. But at state 2, M1 kg of steam leaves the turbine, enters into the heater 1. So the remaining steam, that is 1 minus M1 multiplied by H2 minus H3, this part is the work from state 2 to 3. And the last part, that is the work done by the turbine from state 3 to 4, 1 minus M1 minus M2 multiplied by H3 minus H4. This is the work done by the turbine. Now WP is the total net work by the 3 pumps. That is equal to WP1 plus WP2 plus WP3, because there are 3 pumps are there. So the pump work, that is WP1, is equal to 1 minus M1 minus M2 multiplied by H6 minus H5 plus 1 minus M1 into H8 minus H7 plus 1 into H10 minus H9. Now Q1 is the heat added to the water in the boiler. So Q1 is equal to H1 minus H10, and Q2, the heat given out in the condenser, is equal to 1 minus A1 minus M2 multiplied by H4 minus H5 kilojoule, where WP is called the pump work per kg of steam, WT is the turbine work per kg of steam, and Q2 is equal to heat rejected into the condenser. Now the regenerative cycle efficiency is equal to net work done by net heat supplied. the net work done is WT minus WP whole divided by Q1, because efficiency is defined as output by input. Here output is the net work, that is WT minus WP, and input is Q1. But steam rate is equal to 3600 divided by WT minus WP kg per kilowatt hour, because steam rate, we know that per kilowatt how much steam is required in an hour. So steam rate is equal to 3600 divided by WT minus WP kg per kilowatt hour. Now there is energy balance for heater 1, because the heat transfer takes place for M1 kg of steam and 1 minus M1 kg of steam which is entering into the heater 1. So the heat balance for heater 1 gives M1 H2 plus 1 minus M1 H8 is equal to 1 H9, and if you do little bit algebra, you will find that the final value of M1 is equal to H9 minus H8 divided by H2 minus H8. H2 means the enthalpy at state 2 of the steam. H8 is the enthalpy of the liquid at state 8. H9 is the enthalpy of the fluid at state 9, and M1 is the mass of steam extracted in the first stage from the turbine at pressure P2. Now let us talk about the energy balance for heater 2. In heater 2 is also there is heat transfer. The heat transfer takes place from M2 kg of steam which is being extracted at the second stage at the pressure P3 from the turbine, and that time the enthalpy of the steam which is being extracted from the turbine is H3. So there is heat loss by the M2 kg of steam and gain by the feed water which is coming in to the heater 2. So we can write M2 H3 plus 1 minus M1 minus M2 H8 is equal to 1 minus M1 into H7. And if you do little bit algebra, you will find out the value for M2 is equal to 1 minus M1 multiplied by H7 minus H6 whole divided by H3 minus H6. M2 is the amount of steam extracted at the second stage from the turbine. This cycle is not ideal cycle, as mixing in feed water heater is not reversible. However, with several number of extraction of steam from the turbine that is bleeding, the mixing process become reversible and theoretically Carnot efficiency can be attained. There are some advantages of regenerative cycle. Average temperature of heat addition to the cycle is increased. The thermal stress in the boiler are reduced. The thermal efficiency will be increased. The condenser capacity is reduced. The hotter feed prevents the condensation of sulfur dioxide gases on the economizer. The disadvantages of regenerative cycle are: cost of plant increases, work done per kg of steam is reduced, due to which boiler capacity is increased for a given output. Dear learners, you have understood the regenerative cycle, and we have discussed in detail about the simple power plant where the four components were there: boiler, turbine, condenser and pump. The purpose of the boiler is for producing steam. The high pressure, high temperature steam enters into the turbine, and the expansion of the high pressure, high temperature steam takes place. In turn, the turbine does work. The shaft of the turbine is coupled with the shaft of the generator, which in turn produces electricity, and the low pressure, low temperature steam comes out from the turbine and enters into the condenser. Now, through the condenser coil, cold water is flowing, and the temperature of the steam which is coming out from the turbine is higher than the circulating water inside the condenser. So there is heat transfer from steam to the cold water of the condenser. So the steam will be condensed and the water will come out from the condenser, and that is again pumped back to the boiler. This is the simple steam power plant. But in regenerative cycle, we had seen that at different points there we extract steam from the turbine, and that steam is utilized to heat the feed water. And if you calculate the efficiency, and you will realize that in this way we can increase the efficiency of the steam power plant for the regenerative cycle. So this is the extra heaters which you have to utilize for this case, but at the same time we have to extract the heat at the first time in such a way that after mixing in the heater, that will be the final temperature of the mixture will be as per the saturation temperature of the mixture for that particular pressure. So this is one very important point. And in the next class we will discuss with some numericals, and we will also discuss the binary vapor cycle, and you will see there that the efficiency of the Rankine cycle we can increase again with the help of binary vapor power cycle. But basically you must understand the main theory of the steam power plant, where the four components are there: boiler, turbine, condenser and pump. After that you can think of reheat cycle, then regenerative cycle, then vapor power cycle, then cogeneration plant, and you can see how you can improve the efficiency of the thermal power plant with the help of reheat cycle or regenerative cycle or cogeneration plant or binary vapor cycle. So dear students, today we are finishing this, but let us summarize our today's discussion. We have discussed the concept of regenerative cycle, we have discussed the efficiency of regenerative cycle, and we have also discussed the advantages and disadvantages of regenerative cycle. Thank you very much.